Hello, my name is Alexei Mitin, and this is my investigation into containers or tanks. Idea being that we're looking at how we can optimize volume inside a tank, a container made from a certain sheet metal. So in the original question, we had a sheet metal of 5 times 5, and idea is you need to create a net because you can only bend the metal and cut it. You can't really glue it together. Um, and so it's in the shape of a square base pyramid. Um, there's two aspects to this project. There is this visual representation and the mathematical side. The mathematical side has been explained in the document to great detail. However, I will run through it very quickly here. So first off, you want to ideally create this program to only have one variable that the user can change. In this case, it's this slant height of the pyramid. And so you can see here I can vary this and you have some guiding lines, but these are the ones you will obviously cut by to create this net for the tank. So this slant height will choose or determine rather the base length, which is used in the calculation for the area. And you can see here a lot of values are changing as I change this one variable. So the way this works is that, well, first of all, I chose this here net after experimenting a little bit with different types of nets, and this one is obviously the best one for the square because it's symmetrical like a square. Yeah, it's in the shape of a square to begin with, and there's no what I would call a bottleneck. The bottleneck would be the length here across the square, and that is repeated, of course, here in the symmetrical shape. Yeah, so it could also be rotated 90 degrees, but then obviously you would have less space because the longest side of the square, which is this diagonal, would be used for the straight part here of the square. So this one would be rotated, not 90 degrees, but 45 degrees, yeah? So this one would be rotated 45 degrees, and so this base length here would be horizontal. But you can see the only place where it is the maximum length, this horizontal, is when it's equivalent to the, well, it's not equivalent to the side height, but it's when the height is at its minimum. The reason it has a minimum is because it's the when you fold over the slant heights, it will collapse. So this minimum is determined by 1/2 of the length of the square here, yeah, the base. Because if you're doing smaller than the base, then each corner, the corners of the triangle no longer touch. This is a very bad water tank, you might assume, because it will just collapse in on itself and become a 2D shape in the mathematical sense. So it will have no volume. You can also see here in the program here, it says volume equals 0. And the maximum length is, of course, the minimum length, let's see here, the minimum length is determined by the square root of 50. So that is the square root of 50 is the diagonal length divided by 4, as this base is going to be equal to 2 of these slant heights here. This one right here, maybe should have colored it a little better. So let's say this purple, it's not right. The length inside this purple here, this purple line here. It would be very nice if I could change that. Let's say to blue. Yeah, that you can't see that very well, but this line here. So 2 of these because you have one on each side, and then multiply by 4. So this whole length. And then you have 2 equal sides, which is the slant height. They need to be equal because otherwise they won't connect. And then the square becomes is the size of 2 of them. If I reduce this minimum here, object properties, let me just say the minimum is 0. 0, I can then reduce it, and you can see it breaks its form because the angle here is so wide that it pushes the square, the middle square, outside of the boundaries. You can see here that now they're outside. So this is, if I just Ctrl Z, turn it back. Here you can see that the maximum angle is achieved, which is 90 or 45 if you look at it this way. Let me see if I can, there you go. And so it constructs this square which is two times the length of the slant height. That's the minimum, and the maximum is a half of the diagonal, so 1/2 of square root of 50. And this is because then the square is infinitesimally small, and you really just have these two lines, and it becomes a one-dimensional object or a straight line, also volume 0. We can see here, just by experimenting here, you could choose random values for each of them, and you can try to do trial and error to see, okay, so if I increase these parameters, then the volume goes down, so therefore I should probably decrease them. This program lets you just test all of them out instantly, and you also get a visual representation. You can see here that it seems that the volume maxes out around slant height 2.3, somewhere in that area. We will see a little bit later exactly where that point is. So the mathematical aspects, we have this slant height determining all of the values. The most basic form you can reduce this to is to half of the square root of 50, so you only have 1/4 of this square, and then you're constructing two triangles. So the first triangle is this one here, and then the second one, which would go to the middle here, middle of this here. If I do point, let's say t equals, well, let me do it this way. If I do, then f is equal to 2.5. That's S2.5, what I'm doing. 2.5, and here instead of 3.5 we also have 2.5. 2.5. Then you can see here with the lines, let me just segment these lines here. This would be the most simplest form of this, and you would just have this repeated 4 times. So that's how you can, that's how I did it to simplify it, to first try to figure out how I was going to do this. And so what you get here is the construction right here of these two triangles. You can see here the triangle uses all of the net and maximizes the surface area used, so it uses the most amount of metal, but also it has 0 volume, and then same as at the other extreme, it uses none of the metal theoretically, but then it also gets no volume. So how do we find the best volume to net ratio, or just the best volume for this particular net? Well, we can first we have to define, of course, this here, so that we only have one parameter which decides this the volume, or the area, the area inside the volume the volume inside this tank. So this container will have a certain volume. The volume is defined as the length. So that would be the length here of the base squared multiplied by the height, divided by 3. And the height of the square, or the pyramid here, would not be the same as the slant height. It would be the height of the actual constructed one. So we can see here the height would be 0, and here it would be half of the square root of 50. This we can find by Pythagoras, so we're using the slant height, and the distance here, which is 1/2. Let me get a segment here. This distance here, to get 1/2 of the length of this square. So you can see now that I'm explaining it using using this 1/4 view, and that's just a simplification. Basically everything else is constructed automatically because it's just the repetition of this. You construct the height from the Pythagoras theorem, which is c squared is equal to a squared plus b squared, but this time the c squared is this slant height, so you have to rearrange that to be a squared is equal to c squared minus b squared. So the b squared would be the base, half of the base squared. Okay, that's the kind of parameters here. We have the mathematical side then. That's the volume, right? Length. Let's see, the length is square root minus 2 of the slant heights, which I have denoted by h here, because you will always have these two triangles here. Or if you just look at the 1/4 view, you have this one here, and the maximum distance there in the 1/4 view would be here from the middle here. So the diagonal length from the middle into this corner minus this length here, the slant height. On the real view, you would just double that, right? So you have the whole length minus 2 of this height. And that gives you this length here, or this here, the longer base length for the full one, respectively. There you have the base length, the height, just explained. It's the Pythagoras theorem. And so volume is then we have the length and the height divided by 3. Very simple if you put this into a function. So here is the function for this. You can see if I get 0.0. You can see that I said around 2.3 is going to be the maximum. You can see here that it's very close to the maximum. But to find it exactly, we will use differentiation. So you have here this cubic function. And you can see here that when I change the height, the slant height changes the x positioning, and the volume is the y. So the higher up it is, if I have this line here, okay, so the higher up it is, the higher the volume, and then this is just the slant height. So you can see here 3.5353 approximately is the maximum length we can have, the slant height, and you can see here it's roughly 3.5, and the minimum is 1.76. You see here it's between 1.5 and 1.2, or 1.5 and 2, so that's somewhere close to 1.75. And then the volume here is represented in the vertical. So here you have the vertical, or the volume of 7.7. You can see that this one is pretty high up from 7, but not quite at 8. And this is the function. You take the derivative function of this and equate it to 0. So if I do here, automatically will give it to me. I did this for hand first. Here, you see this orange line is now the derivative function. I'm sorry that the view isn't very clear, but yeah, you see here, there the function is equal to 0. You can see on the original function here, we have a turning point here, which is where the gradient is equal to 0, or it's flat horizontally. That's where this 0 is. So if you equate, if I do the function of x, I don't know if this will return this. If the derivative function of x is equal to 0, no, okay, that does not work. But you do this for hand, and it's a little bit easier. And you can see right there is the maximum right there, yeah, somewhere around 2.3599. This here is actually rounded, so right now we don't know if that's exactly correct. You might have a program that runs kind of more accurately, so you can see there the values get very long, so therefore I just rounded to 5 decimal places as a kind of a estimation. And then we know that the slant height should be roughly 2.35, rather 2.36 to get the maximum volume for this particular square. And so before, I would like to show you part 2 of this problem, or the part 2 of this project rather. I would like to talk a bit about the construction, which is not, it uses math of course, but it's more of the programming aspect to it, and the way I have done it, it would be possible to do it in pretty much any mathematical programming language. This one I use just because it's easy to get the visual representation, and it was a little bit easier to experiment because I can get very quick representation graphically, so I could see when I was doing something wrong, when something didn't make sense. If I want, for example, this one here, this point here, I could very quickly see if something was wrong. So I remember the point was supposed to go down, but it was going up, and that kind of things. So first off, this corner here is just defined as, well, m is just defined as 0, 0. I didn't bother creating any variables for moving this square because it's pretty much irrelevant. So you have j is equal to this corner in the top left corner is just 0, 5, 5, 5, and 0, 5 for k and l respectively. Next, let's take this one here, for example. If I can remember how I did this, E1, no, it's E. Okay, so E1 is equal to cos pi divided by 4. Cos pi over 4 is equal to 45 degrees. So this is done in radians. And from trigonometry, if you multiply the cos, you're getting the adjacent length. So from this angle, I think I have the angles here. Oh, these are 90 degrees angles. Let me see if I can get the angle here. 45 degrees angles. So that was obvious, but you can see that's 45. Can I change this to radians? Object properties, basic angle between. No, this is value. Okay, so I'm not sure where the. Yeah, okay, I can't find the how to explain it, or how to change this to radians, but that would be pi over 4, and then the cos would be the length between, if this is a right angle triangle, this isn't exact now, but this would be the length, this would be the multiple to find the length of this from this slant height. So remember again, the slant height is our variable. So I need to define this length in terms of the slant height. So the way I did this is the cos multiplied by the h, so the slant height. Cos multiplied by the slant height gives us the length here, and that's the x value for this point. So this point is defined as that this length and for the x, and this height for the y, found through the same method for the y is sin of pi over 4 multiplied by h. We will see in the next part the difference when we have a undefined net or a variable net, because then the angles will actually change. Maybe that will be a little bit more interesting for some of you. Here, the next point that is important to define is the second part here. If you remember, we're trying to define two triangles. You can probably further make this easier. So remember, if we had the quarter view, this would be the half of the quarter view or the 1/8 view, and then you're just cutting it along the diagonal, because you really only need to create two triangles, and then you can repeat the triangle here on this side. I know this is all blue, but this one here, and from the middle here, and then you just repeat that 8 times, and then you actually have a fully defined function or a program. So we need to define, just as a reminder, this corner, the middle corner, and then the length between them, those two, so this point and that point, ideally. So here we have 2.5. Because this is a square net, it's never going to change from 2.5. If we had a variable net, it would just always be half of the length, I believe. No, yeah, it would be. So it would always be half of the bottom length there for the x. And for the top length, you can see that this one is below the half. It's actually the square root of 2 length, 2 times the length squared divided by 2. So the square root divided by 2. Okay, so what does this mean? This means that it's 2.5, which is the middle, minus, let's see, minus the length squared, 2 of them, yeah? If I give us some visual aids here, that's that. And we're trying now to find this length here. If I can change its color. I wish I was better at this color changing. No, okay. Color. So let's do green. Okay. That didn't work. Excellent. Excellent, excellent. We're trying to find this this length now, yeah? So that length is equal to the square root of 2 of the length squared divided by 2. The length squared would be a kind of a square, of course, and then we have 2 of them all over 2. So the square root of the 2 lengths, this is the base length, yeah? So this is this whole length here. Well, no, it's this length here. Okay. Here. Now we're going a little bit outside, just for visual representations. So 2 of the square lengths. This square length would be the hypotenuse, and then we square it. The square root of 2 lengths squared. We're doing. We're trying to find this one here. We have cancel. I square root of 2 lengths squared. This one squared multiplied by 2, and then square root that to find, and then have it. I can't exactly remember this, but this would be just Pythagoras again. You can use, and this is your c squared. C squared minus b squared is equal to a squared, and then 1/2 of this length. No, that shouldn't be right. Okay. The square root. No, the 2 times the length squared is it's the whole square, the diagonal of the square, yeah? So the same way that we use square root 50 for this diagonal, this is the diagonal here. So here, this one is equal to the, so this is probably the part that I didn't use the kind of quadra view. Now you can see that I have created a triangle here, and that's what confused me. This triangle here, I found it through here, and then I just halved it, and then if you just cut it, here, then you're getting this length. So that's how I did it. This is kind of what the fun part for me for programming is that you can solve many different problems different ways, and you can see here that I found now just a new way to do it, and that would just be to do this length. So 1/2 of well, I'm doing it. Well, yeah, I'm doing it again, but this is a little bit different. This diagonal, 1/2 of this diagonal minus 1/2 of this diagonal. No, okay, the base length here. This base length, this I to P minus 1/2 of the diagonal length. Then you'll get this one, and that way we have created a polygon here. And we're using the Pythagoras theorem again, rearranging it to solve A from C and B. And B would be this diagonal, which is the whole diagonal divided by 2. Okay, so we have now defined this point, which is what I just explained. It took a little bit too long time maybe. Here, this is the length from the middle here. And 2.5 because it's always half of the bottom length. We have now defined all of them, so we just need to repeat it all over, and then you get the visual representation here. And it's very nice because I can show somebody just the values here. I can just do this, just do that, and then see, well, here I have proved everything. You can kind of see very easily that these values go up and these values go down, but it's not suited for most people. Even for me, it's a little bit dreadful. I might be able to understand it, but it'll take much longer time than just this. You can see that as you increase the slant height, this square in the middle decreases and the triangles increase, and you're using less surface area, but you can't really see that you're using less volume after a certain point, this 2.3 somewhere point. Okay, and so you can pretty much do that into any program and it should work. I went further than my original plan, just to create this one here. You can see here is the values, AC length, the angle is now different. So you can see now the angle is 0.79, and it changes here. Now it decreases. 0.79 is in radians, of course. So if you don't like radians, I don't know what to tell you. You can see here that 1.57, because the angle now is 90 degrees, which is 1.57 is half of pi. You can see now it increases because it's taken from here upwards, here upwards to the center here, and here it decreases because it goes from the, well, it's the same thing, but because it's collapsing now, it's falling instead of increasing, because it goes counterclockwise. That's pretty standard. Again, you can change the slant height. Right now, I just did it for fun, but you can see that it's not limited at its max. I don't know why it's not limited. Okay, it's not limited at all. This was just the kind of default. I remember doing this for fun. It has some nice visuals. It's a bit interesting, but you're breaking the program, because it's not really, this wouldn't be a standard kind of shape that we could make. Maybe this has something to do with multiple dimensions or imaginary number theory, but it's not very practical for us right now. So this is pretty much the same program. If I put the net length to 5 and the net height to 5, you can see we pretty much have the same thing. Just around 2.3 should be our rough estimate for the maximum. The volume is around 8 here at 2.3. This one is a bit more accurate, so it's volume 7 points. Let's see if I can just reduce it to 2.3. 2.3 is 7.6 roughly. Right now it's just over. There we go. 2.3 volume is 6.66. Roughly 3 volume is equal to 7.67. So this one is a bit over, you can see, just because it's defined a little bit different, and it has some finer tuning, but not quite. But it ends at the pi values, or values derived coming from pi. So because it decreases by an increment of 0.005, you're getting some value of pi plus multiple of 0.0005. Yeah. And so the interesting part of this, you can see, and that we can change the value this height, and you can find the volumes for different here, and some small differences in the way this one is defined. This one is a little bit more refined, so you can see it's cleaner. This one here, I like to just keep some of the lines for demonstrational purposes. I very much like having the line, or this triangle here, just kind of for fun, for a visual representation of what is going on. This one has none of that, so this one is the cleanest version, which I did mostly because then you can have this these kind of theoretical ones that aren't practical, and you can see them very clearly and cleanly. Again, if we look at the A is defined as the 0, 0, because I didn't care to move this that much, and then C is defined as net length and net height, so net length for the X and net height for the Y. These are 3 variables: net height, which changes the height of the net length, which changes the length of the net, and then again the slant height, just like in the previous program. Now the differences come here. For example, you have F, this point here in the corner. You can see I have no definition for the middle point. This F is the net length divided by 2, as previously stated, the 2.5 in the previous program, because it's always centered, divided by 2, and then the neck length, the height is going to be the net height divided by 2. So the middle minus, so you remember last time we had 2.5 minus the length here. This one is net height divided by 2, because it is a variable, and then minus the sine of the angle. The angle, let's find the angle. The angle is given by the A, length A, multiplied by tan. tan of net height, oh no, this is arctan, net height over net length. So in trigonometry, you can find the let's say the angle of a certain you can find the angle in a triangle by taking the arctan function of here's the net height and the net length. So of this whole function is this one here and this one here. So tan is of course adjacent opposite over adjacent. Opposite over adjacent. So that's net height over net length. If we create this polygon right here, if I can create this polygon right here, basic trigonometry, and that's how you get this angle here. Okay, there you have the angle. What next? The sine of the angle. So the sine is going to be the opposite over hypotenuse of this angle, so the opposite over hypotenuse, which is going to give us the height here, the for the sine of the sine angle, opposite over hypotenuse is given to the base length. Base length is of course this one here that we have talked about previously, and so we find that this length, if I can create a middle one, let me increase this to 10, and then this one more. There. Give me that point in the middle. We have f being defined as the sine of the angle multiplied by the base length. So then the base length is the hypotenuse from which we are trying to find the this let's see, this segment here. So you have the sine of the angle here coming from this multiplied by the hypotenuse to find this angle, and so you minus the whole length, which is half of the height, so this length there, you can see I can just mirror it here, that this length minus so this height minus this length is gonna give us this height, and you can see that this height is what shows us where the f is, the f point right here. And so again, that's our function pretty much fully defined if you have these 2 points fully defined. Of course you can add just moving this, so if you just change a to be the variable of position, so just position so like if you do position x and position y, and then it'll just construct from that. I believe you'd have to because I didn't test it, I'm not sure, but I believe you might have to add some places where you have certain lengths that must be minus the position in y if there's a change in y, but that's just theory. Again, volume is right here. You can find the volume and you get a visual representation. If you change one of these lengths, you can see that it squishes the pyramid, because this is still technically a pyramid. It's not a square-based pyramid, but it's a quadrilateral-based pyramid, and it still should work. So I find that very interesting, and that has been my CAST project. And so this should be submitted with the document which accompanies it, and it shows kind of the process of me making this.